Welcome to a journey into one of the most fascinating yet underreported breakthroughs in physics and engineering. Today, we'll explore how scientists at Boston University's Photonics Center have achieved what many thought impossible, creating structures that can trap and absorb nearly 100% of sound waves by warping acoustic space itself. These acoustic black holes represent a revolutionary approach to controlling sound that borrows principles from astrophysics and applies them to everyday problems. Join us as we dive into this remarkable technology that doesn't just dampen sound. It bends the very medium through which sound travels. For centuries, humanity has sought mastery over acoustic environments. The carefully designed acoustics of ancient Greek amphitheaters represent some of our earliest attempts to control sound. Fast forward to modern times, and we've developed anechoic chambers and various sound-dampening technologies. But these traditional approaches have always faced fundamental limitations. Porous absorbers struggle with low frequencies, often requiring materials several feet thick to handle sounds below 100 Hz. Resonant absorbers only work effectively in narrow frequency bands, and active noise cancellation systems require complex electronics and significant power consumption. The quest for a passive, broadband, and highly efficient sound absorption mechanism remained elusive until now. The revolutionary insight came when scientists recognized that sound waves, like light, can be manipulated through gradients in the medium through which they travel. In space, gravity bends the path of light near massive objects like black holes. Similarly, engineers realized they could create carefully engineered gradients in material properties to bend, slow, and ultimately trap sound waves. This insight opened the door to acoustic structures that function analogously to their cosmic counterparts, creating regions from which sound cannot escape. Rather than fighting against the fundamental properties of sound waves, these new structures manipulate the medium itself, essentially creating a gradient index that bends sound toward an absorption point. The fundamental principle behind acoustic black holes involves creating a smoothly varying thickness profile in a material, typically following what engineers call a power law taper. As sound waves propagate toward the thinner regions of this specially designed structure, their velocity decreases progressively. This slowing causes the wavelength to shorten and the wave amplitude to increase, effectively concentrating the acoustic energy. At the thinnest point, a small amount of damping material can then efficiently absorb this concentrated energy. The mathematics describing this process is remarkably similar to Einstein's field equations for gravitational black holes. For a plate with thickness following a power law profile where h(r) equals epsilon r to the power of n, where r is the distance from the center, n is greater than or equal to 2, and epsilon is a small constant, the phase velocity of flexural waves decreases as r in 2. When n equals 2, this creates a critical gradient that theoretically traps incoming waves completely. Conventional sound dampening relies on porous materials that convert sound energy to heat through friction. These materials are bulky, prone to deterioration over time, and exhibit poor performance at low frequencies. Acoustic black holes take an entirely different approach. What makes this approach revolutionary is its effectiveness across a wide frequency range without requiring bulky materials. While traditional absorbers may require thicknesses of 1/4 wavelength or more, acoustic black holes can achieve similar or better performance with structures just millimeters or centimeters thick. This represents a paradigm shift in noise control engineering. The latest designs achieve absorption coefficients exceeding 0.98, compared to 0.85 for premium acoustic foams, across frequencies from 400 to 5000 Hz, using structures less than 15 millimeters thick. Recent computational advances have allowed engineers to optimize these structures with unprecedented precision. Finite element analysis coupled with machine learning algorithms has led to designs that overcome previous limitations. The manufacturing challenges have also been addressed through advances in 3D printing technology. Multi-material printers can now create seamless gradients in density and stiffness, allowing for acoustic black holes with optimized properties throughout their structure rather than just geometric tapering. These metamaterial implementations incorporate microscale resonators and precisely controlled impedance gradients that further enhance performance. These acoustic black holes are now finding practical applications across numerous industries where noise control presents significant challenges. In aerospace, Boeing has incorporated ABH structures in nacelle linings, reducing engine noise by an additional 8 to 10 decibels compared to conventional treatments. This improvement is particularly significant given that each 3 decibels reduction represents a halving of acoustic energy. For passengers and communities near airports, This translates to dramatically quieter aircraft. For airlines, it means potential fuel savings as less weight needs to be dedicated to sound insulation throughout the aircraft. In architecture, the newly constructed Philharmonie de Paris Concert Hall utilizes ABH principles in its acoustic design, creating spaces that can be tuned for different performances without mechanical adjustments. The hall's unique acoustic signature has been praised by musicians and critics alike for its exceptional clarity and balanced reverberation across all frequency ranges. Unlike traditional concert halls that might excel for certain types of music but struggle with others, the Philharmonie can adapt its acoustic properties to suit everything from solo piano recitals to full orchestral performances or even amplified contemporary music, all while maintaining ideal listening conditions. Medical imaging has also benefited from this technology. Researchers at Imperial College London are adapting ABH concepts to improve ultrasound resolution by eliminating edge reflections that typically create artifacts in diagnostic images. Early clinical trials show a 40% improvement in feature detection for breast cancer screening, potentially saving thousands of lives through earlier diagnosis. By applying acoustic black hole principles to ultrasound transducers, doctors can now see details that were previously obscured by acoustic interference, leading to more accurate diagnoses and earlier interventions for a variety of conditions. In the computing sector, Microsoft's Project Silica is exploring ABH-inspired structures to control thermal noise in quantum computing components. Quantum bits, or qubits, are extremely susceptible to environmental disturbances, including acoustic vibrations. By implementing acoustic black hole principles at the microscale, researchers have extended coherence times by nearly an order of magnitude, bringing practical quantum computing closer to reality. This application demonstrates how controlling sound at the nanoscale can impact technologies that may define our future computing capabilities. Other applications include vibration isolation and precision manufacturing facilities, where even nanometer-scale movements can ruin production processes. Companies manufacturing semiconductor components have reported 60% reductions in vibration-related defects after implementing ABH-based isolation systems. In industries where precision is measured in nanometers, this technology provides unprecedented stability without the massive concrete foundations or active vibration control systems previously required. The result is more reliable production of everything from computer chips to precision optics, with fewer defects and higher yields. The principles of acoustic black holes are now being adapted for other wave phenomena beyond acoustics. In civil engineering, researchers are developing seismic wave management systems based on ABH principles. By creating carefully designed gradient structures around building foundations, they aim to redirect harmful seismic energy away from structures during earthquakes. Scale models have shown promising results, with up to 70% reduction in structural loading during simulated seismic events. This could revolutionize how we build in earthquake-prone regions, potentially saving countless lives and preventing billions in property damage. Electromagnetic wave control represents another frontier for this technology. Radio frequency engineers have adapted acoustic black hole mathematics to create antenna designs with unprecedented directionality and efficiency. These antennas concentrate electromagnetic energy in specific regions without the bulky parabolic reflectors traditionally required, enabling new applications in satellite communications and wireless power transfer. By applying the same mathematical principles to different types of waves, engineers are finding solutions to problems across the electromagnetic spectrum, from improved MRI machines to more efficient wireless charging systems. As these technologies mature, we may soon see consumer products incorporating ABH principles. Noise-canceling headphones without electronics, quieter HVAC systems, and household appliances that operate almost silently are all on the horizon. Several startups have already secured patents for consumer applications, including a promising design for automobile mufflers that could reduce exhaust noise by 15 decibels while improving fuel efficiency through reduced back pressure. Imagine kitchen appliances that operate in near silence, or air conditioning systems that cool without the constant background hum we've come to accept as inevitable. These everyday improvements could dramatically change our acoustic environment and reduce the noise pollution that affects health and well-being. More profoundly, acoustic black holes represent a philosophical shift in how engineers approach wave control problems, not by opposing nature's forces, but by subtly reshaping the space through which they travel. This paradigm of working with natural phenomena rather than against them echoes principles found in Eastern philosophical traditions and may point toward more sustainable engineering approaches across disciplines. As the ancient Chinese philosopher Lao Tzu might have observed, the most effective way to redirect a powerful force is not to oppose it directly, but to shape the path along which it naturally flows. In acoustic black holes, modern engineering has rediscovered this ancient wisdom, creating silence not through resistance but through the gentle curvature of space itself. This approach may inspire solutions to other complex problems, from fluid dynamics to energy harvesting, where working with natural principles rather than against them could yield more elegant and efficient solutions. Acoustic black holes represent one of the most profound convergences of theoretical physics and practical engineering in recent decades. By borrowing concepts from astrophysics, specifically how space itself can be warped to affect the path of waves, engineers have created structures that achieve what conventional materials cannot: nearly perfect sound absorption across broad frequency ranges using remarkably thin materials. From aerospace to medicine, computing to architecture, these innovations are transforming how we manage sound and vibration. But perhaps the most valuable lesson from acoustic black holes extends beyond their technical applications. They embody a philosophical approach to engineering that works with natural principles rather than against them, shaping the path of forces rather than opposing them directly. As we face increasingly complex challenges in energy, climate, and resource management, this mindset of working harmoniously with natural phenomena rather than forcing solutions through brute force approaches may prove essential. In the gentle curves of acoustic black holes, we might find not just a path to quieter environments, but a template for more elegant solutions to the most pressing engineering challenges of our time. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.